Every major geography textbook establishes a singular origin point for the Ganga River, the Gangotri Glacier at Gomukh. But when we analyze active satellite telemetry from the IRS and Cartosat-3 systems, alongside monitoring records from the Geological Survey of India, a different physical reality emerges. This image captures the high-altitude terrain of the Gangotri Glacier snout. The data confirms this ice structure is actively fracturing and retreating at an average rate of 15 to 22 meters per year. In standard fluid dynamics, mapping a river system relies on a strict axiom. The main body of a river is dictated by the tributary possessing the longest length, the highest water volume, and the largest catchment area. Applying those parameters directly to the terrain, the outflow from Gomukh fails the test. It forms only a secondary tributary known as the Bhagirathi River. The global geographical consensus taught in schools is structurally incomplete. To locate the actual source of the river system, we have to map the physical fluid dynamics further downstream. This aerial photograph highlights the specific coordinates of the Dev-Prayag confluence. Here, the Bhagirathi River physically intersects with a second water body. Looking closely at the boundary line separating the streams, you can see two chemically and physically distinct bodies of water violently colliding. The second stream is the Alaknanda River. It originates from an entirely separate hydrological system, tracing back to the Satopanth and Bhagirahath-Karak glaciers high above Badrinath. Measuring raw metrics at their meeting point reveals the Alaknanda carries a larger catchment area, greater depth, and higher total volume than the Bhagirathi. Because these metrics dwarf the Bhagirathi's output, the Alaknanda mathematically registers as the primary dominant river. Correcting the physical map of the river's volume is a necessary precursor to a far stranger discovery. The specific biology suspended within this water aggressively resists standard decay timelines. Leaving geographical boundaries behind, we must isolate the internal microbiology of the water column itself. Microbiologists from the Indian Institutes of Technology and Banaras Hindu University extracted samples directly from the current to test its composition. This chart plots dissolved oxygen drop-off in standard river water. Standard samples show rapid decline, but Ganga data forms a flat, sustained retention line. For stagnation to occur, oxygen must drop below a specific threshold. As shown, this river continuously avoids that drop. By maintaining unusually high dissolved oxygen, the fluid environment actively deprives anaerobic bacteria of the precise conditions they require to multiply and rot. These peer-reviewed metrics mathematically prevent typical stagnation from occurring. The water operates as a biologically anomalous, self-sterilizing fluid dynamic system. Oxygen retention alone cannot fully sterilize a massive open-air river. A secondary, active physical mechanism is required to maintain this level of purity. That mechanism is an extremely dense, unreplicable concentration of natural viruses specific to this environment, known as bacteriophages. Mechanically, a bacteriophage is a specialized geometric viral structure built exclusively to hunt and eliminate pathogens. The bacteriophage targets a pathogenic bacterial cell, anchors to the membrane, and completely destroys the host, leaving the surrounding ecosystem entirely intact. This hyperdense population operates as an automated biological purification cycle, constantly filtering the water column at a speed and efficiency standard rivers lack. The river is structurally engineered at a microbiological level to continuously hunt and destroy pathogens. Finding the optimal coordinates to tap into this self-purifying network requires a specialized map. Institutional science has successfully quantified this viral payload in modern laboratories. However, the exact geographic grid needed to access these highly concentrated zones was recorded millennia ago. The documentation exists within an ancient Sanskrit text known as the Skanda Purana, specifically within its Kedarkant chapters. Rather than a collection of myths, the text functions as a detailed ledger, listing highly precise, targeted geographical coordinates, collectively known as the Panch Prayag. This map plots the 5 specific nodes recorded in the text: Vishnu Prayag, Nanda Prayag, Karna Prayag, Rudraya Prayag, and Dev Prayag. When we take the exact locations described in the ancient text and overlay the modern IRS and Cartosat-3 hydrological catchment data, the two sets of points align perfectly. This structural alignment confirms the Skanda Purana operates as an advanced cartographic network. It mapped the localized biological anomalies of this water system thousands of years before the deployment of satellite radar. The complete system integrates the corrected physical volume of the Alaknanda River with extreme localized bacteriophage payloads at specific geographic junctions. For decades, standard geographical models failed to accurately identify both the true hydrological source and the internal biological engineering of the water column. Dismissing ancient texts as primitive folklore ignores their capacity to transmit precise, mathematically sound structural data across generations. Modern institutional science is not discovering new, spontaneous behaviors within this river. We are simply acquiring the technological telemetry required to read a fully integrated, functional environmental map that has been hiding in plain sight.